So hello everyone. So today we'll try to understand how to visualize the speech signal in time domain and spectral domain or in frequency domain. What are the ways of visualizing it? What are the software exist, and also the mathematical representation of it. Okay. So let me just go through the. Let me just tell you the software that are required. The mainly, most importantly, the widely used uh, software is Pratt for speech visualization. So you can search for Pratt and you'll get the downloadable file. So it is developed by the Paul Boersma and David Winning of University of Amsterdam. Now, uh, although we have different Python libraries to for the visualization of the speech signals, so still we have a ready-made software. So let us just go through it, try to understand how to visualize the speech in time and spectral domain and other representation of speech. So we also have Audacity. So Audacity is basically used by different, people who work in music processing, speech processing, for mixing of sound, for mixing of noise, background noise. Even it can be also used for leveling the specific region of the speech. So let me just open Audacity first and let you just visualize how speech looks like in audio as a time domain. Now let me open an audio file. So you can see this audio file is the amplitude and the time. Okay, so I have a 5 second of around 6.5 second of audio sample. Now as I already discussed in my earlier lecture that how the glottal impulse get multiplied with the response of the vocal tract and we get the final speech. So it is something it's something like let me download the previous slide such that I can do the explanation over here. So it was my till what I have discussed in my last discussion. So let me just download it and make you understand here. Okay. So here we have discussed the last slide that so this is the vocal cord. So when the air flows through it, due to the vibration in the vocal cord, we get a glottal impulse. So in time domain, the glottal impulse looks a bit, it looks a bit periodic wave. So the glottal impulse is in time domain, it has some periodic nature or something like this kind of pattern you get. This is a glottal impulse. Now this is the vocal tract, and based on the shape of the vocal tract, as I have already mentioned that this vocal tract is a time varying function. So it varies over the time, and due to the different shape of the vocal tract, we get different sound. Now say for example I am uttering a specific vowel sound, and the vowel sound, the pattern in time domain looks like something like this. Okay, so once you get the output speech, so it may say for example it looks like something like this. Okay, now if you do the Fourier transformation of this glottal impulse and this vocal tract response wave representation, the time domain representation. This will do the Fourier transformation. It is a xt, it is ht, and it is say for example s of t. Now you can see over here st is nothing but x of t multiply with h of t. Okay. Now if you do the Fourier transformation, then you get something like this. So you'll get different frequencies. Yeah. X, 0, omega. Okay. Now, if you multiply with, say what this is the Fourier transformation of h of j of, then we get, multiplying with this, the final power spectrum of the final speech. Okay, so and this is the s of j of omega. Okay. Now I can write also over here, then s of j of omega is nothing but multiplication with the glottal Fourier transformation of the glottal impulse x of j of omega multiplied with h of j of omega. Now if you do the power logarithmic power representation, then what will happen, we can separate out these two part. Okay, so if you do log of this part, then you get log of this Fourier transformation of the amplitude of this x of j of omega, that is the glottal impulse, plus log of this part. This is the vocal tract response, Fourier transformation of the vocal tract response. This part. Now what will happen? You can see that. So now you have the power spectrum. So say that the power spectrum looks something like this. Okay, something like this. Okay, the final speech. These are from glottal impulse. The logarithmic power spectrum, say for example, like this only. And logarithmic power spectrum of this vocal tract response is, or impulse is, vocal tract impulse is something like, say for example, this one. Now, what is happening over here? So I can simply say that this wave file, this logarithmic power spectrum plus this is nothing but is equal to this one, isn't it? The final representation. So that is the reason why we usually do logarithmic power spectrum. So it helps us in understanding, separate out both the glottal part and vocal tract response. This is the h of t, h of j of omega. Okay. Now the same thing we are going to will try to understand from the visualization part. Okay. Before that, let me just tell you what a periodic signal and quasi-periodic. Why I am saying that the speech is the quasi-periodic signal. Now, as I have already shown that the glottal part is kind of a periodic signal. Okay, and this is a kind of quasi-periodic. So now let me just visualize a specific region of it. So now you'll be able to see that there are certain kind of patterns, and it is a repeating pattern. Okay, you can see this kind of repeating pattern over the time. Now, though you'll find that this though there exists the repeating pattern, but it evolves over the time. This patterns, the periods. Now, it is not that this is the reason why it is not a you know uh, proper periodic signal. It is rather it is a quasi periodic because the periods of evolves over the time. Now, if you see you're trying to visualize the spectrum, the formants and all in pred. Now you can do it by opening the audio file. So I'm opening the same audio file from my system. So here I can view it. So initially I'll try to view the only the say for example only this part, the spectrogram. Okay, so this is the spectrogram representation of the audio signal that I have just shown you. Now I have already mentioned the spectrogram gives you a glimpse of an idea of how the frequencies are changing over the time and their amplitude as well. Now if you plot the formants, see this is this red color of pattern, continuous pattern that you can see over here. So you'll find that there are not many patterns. Mainly there are 3 to 4 patterns are there. Okay, continuous pattern. Okay, throughout the time. And these are called the formants. So you have the first formant. Okay, so it is going from this. It is changing from this lower part to the extreme end. Then just before it you have the second format F2. It is also changing over the time. Now if you try to find the intensity, so I'm just erasing out other things. So this is the intensity. So this is nothing but the kind of Fourier transformation. It is a Fourier transformation of the xt. There is a audio signal. Okay, and if you want to see the pitch, okay, so you can see the pitch over here. Okay, this is the kind of fundamental frequency. The fundamental frequency that is changing over the time. Now there is something called cepstral analysis. So what is it? Now as once you get the final speech and you do the logarithmic transformation of power transformation, okay, or logarithmic power spectrum, so you get this glottal part and the vocal tract part. Now you will see that I want to do the smoothing of the final power spectrum, logarithmic power spectrum, this part, because it looks something like this. Okay, let me draw it properly. Because it looks something like this. So I want to get the smooth representation of this continuously changing pattern. Now as I've already mentioned that this s of log of s of j of omega is nothing but the summation of two parts. One is, say for example, the glottal part, and it is somewhere here. Say for example, it is somewhere here, and this part, and the vocal tract part is somewhere in the upper section. Say for example, it is over there. Now summing up this one and this one, say for you are getting, so So I've done some mistake over here. Yes. Okay. Now summing up this part, and say for this part you are getting the final result. Okay. Now I want to get a smooth representation of it. So how I can get that? Now for a simple you know addition of two signal, I can make you understand this. Say for example I have two signals, the power spectrum, logarithmic power spectrum, similar way as j omega, this log of e of g omega and h of j omega. Now if you have, let's say for example, if you have a higher frequency in the mid part, you have a smooth representation of the changing over the time frequency. There is a smooth curve, okay, not changing over the time. So these have the higher frequency because it continues changing over the time. And you have, say for example, another frequency, something like that. Okay. Now you can see that if you do the Fourier transformation of it, you will get some high frequency, this part, and for this you will get some low frequency. Okay. Now if you sum these two frequencies, okay, just similar to that of the logarithmic power representation of this h s of j omega and e of j omega, the similar way will get this part. There is the s of j omega, the final one, isn't it? Now final one will be having this one and this part. Okay, but I just want this smooth curve, this smooth representation, not a continuous representation. I mean continuously varying plot. I do not want that. Rather I just want this lower part. So how we can do that? Because it is now having these higher frequencies and the lower part also. So for that purpose we must have to use some low pass filter. Okay, so that we can do in inverse Fourier transformation. Okay, so once you do the Fourier transformation, so what is happening basically? So initially we are doing what? Fourier transformation of s of j of s of t. Fourier transformation of first Fourier transformation of s of t. Then you will get s of j of omega. So once you get s of j of omega, means this part, you are using log of power. Logarithmic power spectrum. You are getting the logarithmic power spectrum using logarithmic transformation of the x of j of omega. Okay. After that you are using, say, inverse first Fourier transformation IFFT to get smooth representation of this continuously varying plot. This one, okay, a smooth representation. Say for example something like this. Then the plot that you are getting is called cepstrum. It's not spectrum, but as after inverse Fourier transformation, it's called cepstrum. Cepstrum, and it's called cepstral analysis of the speech, ST. Now when you have the cepstrum, this part, this x-axis is no more frequency, it is quiescency, Q-U-E-F-R-E-N-C-Y, quiescency, and here you get the absolute magnitude. Okay, so this is a specific kind of transformation of speech, so using which you can get the if you do the male filtering also, then you will get the male frequency cepstral coefficients. So there is a specific operation that you can perform, then male filtering, So using our male scaling basically in between in the intermediate part that I'll discuss later videos. So we'll get the male frequency substral coefficient also. So this is nothing but you are getting just the substrum or substral representation of the speech. You can also get the male frequency substral coefficient that often used as a speech feature in speech recognition. Synthesis it is not much used, but for recognition it is widely used. Okay. Thank you.